Okay, let's begin. First of all, on the homework, GHW number 11, you can have, in fact, you may prefer to hand it in tomorrow. You can hand it in up to tomorrow. You can hand it in today if you like, but you can hand it in at any time. There'll be a box in the front window in mathematics. Okay, so it'll be Maths 108. It's the downstairs, the business window. I'll have a box there. You can hand in the homework. In some sense, I prefer that you did actually wait and revise, because in fact, more or less what we're going to discuss today is that homework with that particular problem. And I, in fact, have graphs for you here to look at. I use slightly different numbers here for the values of the coefficients, but all the ideas are the same. And I'd much prefer that you digest what we have to say today and then do or redo the homework and learn it very well, rather than have you try to just hand it in without feeling that you've understood everything. Okay. So, what's the goal? What are we doing here with these kind of equations? They turn up quite often. Systems, they're very general equations. The only special thing about the equations 8.1 is that the equation itself contains no term with the independent variable t explicitly. So in other words, dx by dt is some function of x and y, dy by dt is some function of x and y, and not t. There's no t there, so therefore they're called autonomous equations. Autonomous equations. And the example we're going to take is the one for rabbits and foxes. Let me remind you again that in fact the equation for the rabbits and foxes here, x is, say, as measured in fractions of thousands, say, and y is the population of rabbits. Rabbits grow at a certain rate. You'd have a certain rate constant, so dx by dt would be k1x. But you can eliminate the constants. There'll be 6 free constants altogether. But by rescaling x and y, as I have shown in the notes, you can get down to just 3. And I call them here E, F, and G. We've called them gamma, beta, and alpha in some of the previous times we've written this down. But because the JODE only takes Latin letters, we're going to use E, F, and G. The reason I'm not using A, B, C is we're going to be using A, B, C, D a little later today in another context, so I don't want to confuse the meanings. So this basically says rabbits left to themselves will grow exponentially. If they meet foxes, if there's foxes in the environment, then they lose their population because the fox eats them. But if there's no foxes, then, and there's no culling, then there's a natural saturation of the population. In other words, without these two terms, the population would grow to a size 1 over e, and then would stop. Now you've actually examined, before we've examined equations such as this. dx by dt is just some function of x, and we solve essentially by doing graphs. And just looking where the graph is positive and negative, we can tell exactly what the solution is going to do. E then is related to the saturation, to the number of rabbits that the environment can sustain. And F is some culling. Either you're handing out hunting licenses or you're poisoning the poor rabbits. Okay? That happens. Actually, I was just telling some people in the special class the other day that on NPR on Monday, I think it was, I heard about a problem with ferrets in South Dakota. Anybody here from South Dakota? You are? Well, you had little trouble with your ferrets recently. I'm not sure that you knew about this, but apparently the ferrets eat prairie dogs. So the prairie dogs are like the rabbits, the ferrets are like the foxes. And what they found was they were culling the prairie dogs because the farmers don't like these holes in the ground and churning up the land. So they culled the prairie dogs too much, and then they actually lost the ferrets in the state. So they were starting to try and reintroduce them again. So sort of considerations of these equations will tell you how careful you have to be in actually controlling this environment. This is the equation for the foxes, the predator. It's proportional to if the foxes, if there's no rabbits, the foxes will die off because there's no source of food other than rabbits for them. But they meet rabbits occasionally and chew them up, and that's how they get fed. So we have these two equations for a very realistic situation. And so now how do we go about finding information about what the solutions do? Well, we would like to solve x as a function of t and y as a function of t. And if we do, then we can draw the position of the pair x of t, y of t, as t evolves, and that'll make curves in the xy plane. It's called the phase plane. Those curves are described by this equation. This equation is derived from these essentially by using the chain rule. dy by dx is dy by dt, dy by dt is g, times dt by dx. But dt by dx is 1 over dx by dt, which is 1 over f. So that's how you get the g over f. Here, I've just put down what they are in the case of the example. Now, the first thing you try and do is you identify the equilibrium points. What are the points in the plane where these are 0, both 0? Okay, so you want both the f and the g to be 0. Because if that's the case, then dx by dt is 0, dy by dt is 0, and x and y don't change. But knowing the fixed points or equilibrium points is only a little bit of the story. You really want to know what's going to happen in the whole xy plane. If you start with this many rabbits and this many foxes, what's going to happen? What's the outcome? These are the questions you would like to answer. Well, if you could solve this equation, the trajectories in the xy plane are described by this first order equation. Now, for instance, if this were separable, if it was one of the first order equations you can actually solve analytically, and we've done some examples with balls sliding in wells where that's been the case. We also did the pendulum example where you have no friction, then you can solve this equation. In this case, if E was 0 and F is 0, then actually the equation is separable and you can solve it. The solution is kind of complicated. It's something like x plus y plus log x times y equals constant. But in principle, you could draw those curves in the plane and learn what happens. Okay? But we're more interested in having a saturation, and we are particularly interested in the question of how much culling should be allowed in order to maintain a stable ecology, a stable environment. That's the question we'd like to address. So, the approaches is identify equilibrium points. Well, we've done that. We'll do that now for this example in a moment in particular. Then if we can, we'd solve this guy. Most of the time, you won't be able to solve this guy by analytical methods. All right, then. So what do you do then? Well, in all cases, we use GAODE. We let the analysis guide us, but using the software to solve these equations and draw the trajectories in the XY plane is by far it's a very important step. It's a very important part of the investigation. So you would always go to some JODE or some other software. Most software and systems of autonomous equations, most software covers solving these sorts of equations. Now, what do you do though? If we only can solve and get the fixed points, if that's the only analytical thing we can do, that's not quite enough, because you really need some analysis in order to make sure that you're understanding what the actual numerical solutions are telling you. So we do a little bit of a compromise. We say, okay, we can't solve the full equations, but what we'll try and do is we're going to look near the equilibrium points. Okay, we're going to look near the equilibrium points and ask, what does the solution do if we start near the equilibrium points? Does it go back to the equilibrium point? Does it just stay in the neighborhood? Does it go away? Or what does it do? So this is the analysis we're going to cover this morning, the local analysis near these points. Now I'm going to now do it in more generality than we've done it in the context of those particular examples we've looked at before. So we want to solve, we want to look at x close to, so we want to set x to be xe plus big X. And we're going to think of big X as small, meaning that big X is much bigger than big X squared or big XY, where we set y equals ye plus capital Y. We're going to think of these guys as small, and we're going to derive equations for those guys. Those guys, we'll see, will satisfy linear equations, which we can solve. The linear constant coefficient equations, we can solve them. And therefore, we are going to be able to find out information as to how the solution of the fully nonlinear problem, the full problem, behaves close to the equilibrium points. So the idea is that if you know the equilibrium points and you know how the solution behaves in the neighborhood of equilibrium points, you can more or less check out, you get a very good idea of what's happening in the whole phase plane. The other thing, of course, you can use direction fields. And you can see on your JODE all those little arrowed fields. Those little arrows are just the tangents. You can calculate this at every point, x, y, as long as both g and f aren't both zero simultaneously, namely at the equilibrium points. But everywhere else, you can calculate this and put a little arrow in the right direction. So you get a very good idea just from the arrows what the field looks like. For instance, this is now the JODE where I've taken E equals E equals 0.4 and F here. F is equal to, I think, 0.2 here. And you can see sort of the arrows give you the directions. This is the tangent of an angle. The arrows are drawn in that direction, and the little end of the arrow points in the direction that the solution will move as time increases. All right, so that's we will come to more analysis of this later. So that's the JODE, and we're going to be particularly interested in the behavior near these fixed points. And now the first thing we're going to have to find out is the fixed points. In our example here, what are the fixed points? Well, in order for this to be 0, x can be 1 or y can be 0. If x is 1, putting x equal 1 here, y is 1 minus e minus f. So one fixed point is this. Another is when y is 0. When y is 0, this disappears, and now we're back to this quadratic equation, and the other fixed point is 1 over 2e, 1 plus or minus 1 minus 4ef. That's the x component of it, 0. So on our graph here, here's the fixed points. This is the 1 minus e minus f, and the other fixed points are here and here. Okay, they're roughly 0.25 and 2 and a bit. They're roughly there and there on the y equals 0 axis. So they're the fixed points. So now we're going to examine the nature of the behavior of the solution near the fixed point. So I'm going to write equations for this guy. This guy is dx by dt, because dxe by dt, xe being constant, is 0. So this is just f of xe plus capital X, ye plus capital Y. dy by dt is g of xe plus x, ye plus capital Y. And now, up to now, we have the same equations as we had before. But now we're going to make an approximation. We're going to think of x and y, the big x's and big y, as small. So we're going to expand this out in the Taylor series, which is just this, x times df by dx at xe, ye, plus y df by dy at xe, ye, plus terms which are x squared, xy, just the higher terms in the Taylor series. But we are going to ignore them because we're just going to imagine that we're close to where x and y are small. Similarly, with the g, I have this. At xe, ye, plus, again, quadratic and cubic terms in higher order. Okay, but now, this looks a bit complicated, but it's very simple, because we are forgetting about these. So we forget about these because the quadratic terms are, in general, small compared with the linear terms. This guy is a big fat 0, as is this guy, because xe and ye are equilibrium points. These coefficients of big X and big Y, these are just constants. You just take the partial derivative of f with respect to x, evaluated at xe, ye. We'll do that now in a moment for the example. So this I'm going to call A. This I'll call B, this I'll call C, and this I'll call D. Okay? So now let's calculate, in our case here, what they would be. What is df by dx? Okay? For our example. So what is the derivative of f with respect to x keeping y constant?
That would be 1 minus y.
Very good.
Minus 2e x.
Very good. Now, the next man, what is df by dy? Negative x. What is dg by dx? Man in the green shirt. It would be g, it would be plus, you see the term with x in it is plus gxy. So it would be g, gy. And what is dg by dy equal to?
Negative g, 1 minus 20, 1 minus.
Very good, very good. Okay, now let's evaluate this at the fixed point, this fixed point. 1 minus e minus f. Okay, so could you all just calculate what would 1 minus y minus 2ex be if you take x equal 1, y equals 1 minus e minus f? So 1 minus e minus f minus 2e. It's very simple. Actually, it's just f minus e. So it's just constants, the difference in those two, f minus e. What is the value of df by dy at x equal minus 1? I mean x equal 1. Just minus 1. What is g times y at the equilibrium point? It's right, it's g times 1 minus e minus f. Now, who's going to get this one? What is this coefficient? Big fat 0, because x is 1, right? So, in that case, this is our A, this would be our A, this would be our B, this would be our C, and this would be our D. Now, I have worked out all these coefficients for you on the front page here. I've worked them out at the fixed point 1 minus e minus f, and I've worked them out at the two other fixed points. Okay, so now our job is to analyze this very simple equation. What's the simple equation? dx by dt is a times x plus b times y. dy by dt is c times x plus d times y. Linear constant coefficient equation, yes.
So how do we change d little x dt to d big X dt?
Okay, you take the d by dt of little x is equal to xe plus capital X, right? But xe is just a constant, 5, here 1, right? Okay, the d by dt of that is 0. So d little x by dt is the same as d big X by dt. Right? Because the little xe and the little ye are constants. They don't change in time. Okay. So now we have the equations. I'm going to just simplify them, write them down.
Does it matter what order you put A, B, C, and D in?
No.
You took the partial g on that A.
No, it doesn't matter at all. No, that's just what you call things. The reason I introduce A, B, C, D is it's easier than to write down df by dx at x, e, y, e. So it's a shorthand notation. It's just, okay. So now I have these two equations. dx by dt is ax plus by. dy by dt is cx plus dy. These are just constants. In any particular case, you have calculated what they are. This would be the A. So in your example, I think I gave you this was 0.2 and this was 0.1. That was the first one. So your A would be minus 0.1 in that case. Okay, but we're just working it out for any values of the A, B, C, D. Now, if, to solve these equations, if both b and c were 0, this is gone, then they're very easy to solve. dx by dt is ax, x is just x naught e to the at, and y would be y naught e to the dt. So you can figure out what the system is doing exactly just from a and d in that case. Okay? In most cases, that's not going to happen. Let's assume that b isn't 0. For b not 0, I can solve for y is 1 over b dx by dt minus ax. Now I shove it in this equation. I could actually just solve straight away here if we had done our linear equations as matrix equations, but we haven't. We've done them as scalar equations, so I'm converting this pair into a second order equation which you will recognize easily. Okay, so y is this, shove this in, dy by dt, so I have 1 over b d2x by dt squared minus ax, minus a dx by dt, because I'm taking dy by dt, then that's equal to cx plus d over b dx by dt minus ax. Now we'll just clean that up, just put everything together. We've one term d2x by dt squared. I'll multiply across by the b. Then I'll get a minus a plus d dx by dt. When I multiply across by the b, I have a minus a dx by dt here. And over here, I have a d times dx by dt when I multiply across by the b. Bring it across the left-hand side, it's minus d dx by dt. And then finally, I'll have a term minus AD on this side times x. Bring it across, it'll be plus AD times x. And then minus BC times x equals 0. And the y, of course, is just dx by dt. But you see, this guy is a homogeneous, second order, linear equation with constant coefficients. Constant coefficients. One coefficient is this, and this is this. So now to just again shorten my notation, I'm going to call this guy P. I'm going to introduce P as minus A plus D, and Q is AD minus BC. Okay, and now the equation we have to solve is very simple. It's d2x, no, I want to work on the top board here first. It's d2x by dt squared plus p times dx by dt plus qx equals 0. And we have that y is dx by dt. Sorry, no, that's not true. Y is 1 over b dx by dt minus ax. Okay. Yes?
On the left-hand board, the second to last line on the far right next to equals 0, that's equals 0 comma y equals
Yeah.
dx. Y equals dx dt.
Here. Okay, that's wrong. That's wrong. That's wrong. Pop, pop. Sorry. Yep. Y is equal to this. I mean, it's only if the a was 0, it would be dx by dt. So I hope I didn't make that mistake. No. Good. Yeah. Okay. All right. But now, this is now revision for the second part of your course. We want to solve homogeneous equations, which are linear, constant coefficient, and the p in this case, for instance, what would the p be in this case? The p is minus a plus d. So it's just e minus f. What's the q in this case? The q is AD 0 minus BC. So it'd be minus 1 times this. So it's G times 1 minus E minus F. So for this fixed point, the P is this, and the Q is this. And these are numbers. For instance, in your case, the first case, I'll come to your question now in a minute, E was 0.2, F was 0.1, G was 2, 1 minus E minus F would be 0.7. Question?
That equation there, that second order homogeneous one, is that going to be of the same form for any pair of non-homogeneous?
Yes, yes. I'm glad you raised that point. The equation for the x here, if I said, no, I'll try and write down the equation for y instead. So I'll solve for x from here in terms of dy by dt and y, shove it in here. I will get the very same equation for capital Y as I got for capital X. In fact, I'll get the very same equation for any combination of cap X and cap Y. And the reason for that is that any combination of those is just a transformation on the vector xy. In such a transformation, this matrix A, B, C, D, that matrix has two invariants. Its trace, which is A plus D, and its determinant, AD minus BC. That's just for the folk. Yes, you haven't done the linear algebra yet. Yes?
So in this homework, we're supposed to actually have constants that we plug in to E, F, and G then?
Right.
So which ones do we use?
Well, you have 3 equilibrium points, right?
Yeah.
So you have to test each one.
Well, I mean...
We're not finished yet.
Constants, though. What constants?
Oh, well, whatever you were told E was 0.2. E is the gamma. E is 0.2, F is 0.1, and I think the thing we called alpha, or the thing we called G, was 2. Right? That was the first one. That's this one. Okay? Except in this case, I've used E is 0.4, F is 0.2, and I took G equals 2. Okay? I don't mind if you turn in, as long as they're your graphs, not mine. Okay? All right. So now, how do we solve this? How do we solve this? Well, x equals e to the RT. Right? Shove it in here, and I get r squared plus pr plus q is 0. Or r plus or minus, the two roots are minus p over 2, plus or minus the square root of p squared over 4 minus q. Okay. So now I have the following. The solution then would be x equals a e to the r plus t plus b e to the r minus t. And the y would be, of course, 1 over b dx by dt minus ax, which you can work out. It'll have a similar form. Okay? So now we have to sort of talk about what are the values of the r plus and r minus. What are the possibilities? Okay, well, case 1. P squared over 4 minus q is greater than 0. Okay? That means the two roots are real. The two roots are real. Because this is real. Now case 1a is I'll take p squared over 4 minus q is positive and q negative. Q negative. Certainly that is true if q is negative. But what's important to realize is the signs of the two roots are now opposite. There's one plus guy and one minus guy for any value of p. Do you see that? It doesn't matter whether p is plus or minus. Let's start with it plus. This would be plus times the square root of p squared over 4 minus q. But if q is negative, this guy is bigger than the p over 2. Okay? So I'd have a minus something plus something which is bigger than this. So that's the plus root. R plus would be positive. Then R plus is positive and R minus is negative. So now what are we going to find? We're going to find that x is this and y will be something like, when you work out what that is, what would it be? It would be 1 over b dx by dt will give me an r plus and then minus a times capital A equal e to the r plus t, and then I'd have 1 over b r minus a times b e to the r minus t. Right? But now the r plus is positive, the r minus is negative. So, in one very special direction, for instance, if I chose my initial conditions, if I start near the point xe, ye in such a way that the b is 0, no, sorry, we'll first of all take the a 0. Supposing we start with initial conditions on capital X and capital Y. On little x and little y, they'd be close to xe and ye. Okay? Then, if I chose initial conditions such that the a vanished, then capital X, capital Y would decay because r minus is negative. It would decay as time rolled forward. That we call the stable manifold. Okay, the stable manifold. This is an unstable saddle. So this is an unstable saddle. And I'll come back next day, we'll talk a little bit more about stable and unstable manifolds. Unstable saddle point. So now, on our PQ, in the PQ plane, we have this graph. So this is PQ. This isn't XY, this is PQ. One interesting curve is P squared. This is P squared equals 4Q. Now, right now, in case 1 and 1A, we're operating where P squared is greater than 4Q, so we're operating outside of this parabola. Here and here. The case 1A, we took Q less than 0. So anywhere over here, whether P is positive or negative, we have unstable saddles. And each of them have these things we call stable and unstable manifolds. If you remember, they divide up this phase plane near the unstable saddle point. Okay, so that's case 1A. How about if the Q was positive? We have P squared over 4 minus Q is greater than 0 and q is positive. Now we have two roots which have the same sign. So r plus, r minus, same sign. They are both negative if p is positive. Right? Because this guy now is less than the size of this. Think of p positive. So both roots would be negative. So then, as time evolves, you will just go back, straight back to the fixed point. So in this part of the plane, where p is now positive, and p squared is greater than 4q, so up here you have a stable node. If the p is negative, then both roots are positive. So down here, you have an unstable node. This is acting like a very strong friction, if you like, in the example of the ball of the puck sliding in the hill. This would be like an amplifier. Maybe you'd have some lasing amplification going on. Now the next category, case 2, would be where p squared over 4 minus q is less than 0. Now the two solutions are x equals a e to the minus p over 2t cosine q minus p squared over 4t plus b e to the minus p over 2t sine q minus p squared over 4t. Right? Because now the roots r plus are complex conjugates. R plus is minus p over 2 plus I times the square root of q minus p squared over 4. And r minus is minus p over 2 minus I times the square root of q minus p squared over 4. Now, if the p is positive, if you're up here, x will go to 0, y will go to 0, the capitals. So little x and little y will go back to xe, ye, but they'll spiral back in because of the cosines and sines. So this is a stable spiral. And this is an unstable spiral if the p is negative. If p is 0, right along here, p is 0, we call this a center. Now, let us look at our example. Okay, so now here in our example, we're looking now at this fixed point. This fixed point. The p for this fixed point is e minus f. The q is g times 1 minus e minus f. But 1 minus e minus f, that's positive because it's in the, you know, if it was negative, you'd have less than 0 foxes. Okay? 1 minus e minus f is the fraction of 1,000 of foxes that exist at this fixed point. Okay, so in the first example, here it's e equals 0.4, but in your first example, it was e was 0.2, f was 0.1. What's the sign of p? Positive. What's the sign of q? Positive, because this was 2 and this is 0.7. So where are we? Here. Okay? Well, we don't know whether we're actually here or here. But we can check, is p squared, you could check if p squared is greater than 4q or less than 4q. But in any event, if p squared was greater than 4q, which isn't going to happen actually in this example, okay, for the numbers you have, you're going to be down here. I mean, you're up here if p squared is greater than 4q, but I'm telling you for these numbers, that's not the case. You're going to be here. So you have a stable spiral. Now, look at this. Look at this. I started near here, okay, and we spiral in to this fixed point. That's the JODE. Okay? We start and spiral in. Now, what I'll find is if I do the same analysis, at the other fixed points, the other equilibriums, the ones on the axes, I'm going to find that both are on stable saddles. For both, the Q will be negative. So you're in the left-hand side of that plane. This picture, by the way, is on page 24 of lectures 20 through to 30. Okay, now, next day I'm going to talk a little bit more about this guy. This is a superorbit. What this guy is, if I look at the stable and unstable manifolds of this unstable fixed point. Now, this unstable saddle, remember, the stable manifold is the set of initial conditions which if you start at, you will end up going into that saddle point as time goes forward. To find that path, what you do, and I bet you, did anybody think of doing your time, putting the time from say minus 60 to 60? Because if you go from, see the trouble is if you start down here, near here, and go forward in time, you'll just go bang in there. Or maybe if you're not quite on it, you'll swoop out here and go into the spiral, or else go down to 0. But if you want to go backwards, if you want to find this whole unstable manifold, actually put minus 60 to 60, and then it'll run the trajectory backwards. It solves the equations backwards in time. Now, I want you to look at this. Is very important. Very important. Because look, see that big black line there? Now, wouldn't you think, let me draw it here roughly on the board. So here we are. Here's one unstable, stable, here's the other one. And so we have this, what I call the stable manifold. Start anywhere on this, you end up at this unstable point here. Okay? But now, supposing you're to start and you can see a trajectory above it. Look at the trajectory above it. I'm going to start out here with zillions of rabbits. Zillions of rabbits. And I could even put in lots of foxes too. I could start up there. Millions of foxes and rabbits. Now, wouldn't you think that would be a grand way to start your environment? If you have lots of them, no problems. You do have problems. Because where did that trajectory end up? Huh? This one out here, it went bang. You lost your whole ecology. You lost your rabbits, you lost your foxes, you lost everything. Okay? So the basin of attraction, the set of initial conditions which will end up at this stable equilibrium here, is the shaded part under the unstable manifold of the left-hand unstable saddle. See, this is really lovely. I mean, it's very hard to understand this. Now, well, what would happen? If you have lots of rabbits here, lots of rabbits, you would think, well, the rabbits are safe. Well, they're not. Because if you have lots of rabbits, the plus GXY term up there, there's lots of rabbits for foxes to eat. Right. And if there's lots of rabbits for foxes to eat, the fox population will grow. And that's what it does. It shoots up like that. But the trouble is it shoots up so high that now you've eaten a lot of rabbits and you have a huge number of foxes. So even though you don't have that many rabbits around here, the product of X, Y is still big. So I'm afraid that's it. That was a very bad choice. If you introduce into your environment so many rabbits and so many foxes, not in the basin of attraction of where you want to go, too bad. That's going to cost you thousands of rabbits and thousands of foxes. Right? That's not immediately intuitive, is it? You would think if you have lots, but when you think about it, if you have lots of rabbits, you make lots of foxes, and if there's too many foxes, there's lots of foxes to eat the rabbits. And so now, what do we think happens? So now I've changed on this graph, just on the other side of the first one, I've taken now my culling, I've increased the culling. I've increased the culling. I keep the E still 0.4, but now the F has gone to 0.3. Now notice that the number of foxes at the fixed point has gone down, because now 1 minus E minus F is 0.3 rather than 0.4 as it was in the last picture. Sorry? What's culling? Yeah, well, it's removing rabbits from the scene. You can either remove them by handing out hunting licenses, and guys like you with guns will shoot them, or farmers poison them. Because particularly, I was telling you about the prairie dog situation. The rabbits and the prairie dogs were the prey. The prairie dogs are a nuisance. The farmer poisons them. Now the food for the ferrets has disappeared, and so the ferrets go as well. So that's so culling means essentially you're taking out so many foxes or so many rabbits from the environment per year at a fixed rate. Okay, so now we have increased the culling here. What do you notice about, what's the difference between those two pictures? First of all, the stable fixed point is lower for foxes. It's still 1,000 for rabbits. It's still x equal 1 for the rabbits. But for the foxes, now it's 1 minus 0.4 minus 0.3. So it's 0.3. So that's certainly true. But what else is happening here? What else do you recognize as happening? The basin of attraction has gotten smaller. Look. Yes?
Can you go over exactly the basin of attraction is?
Yep. Okay. It's the set. When you have a fixed point which is asymptotically stable, in other words, things get attracted to it, then it's natural to ask, what are the set of initial conditions that if you start the system there, it'll end up going to that fixed point? So that's called the basin of attraction. It's the set of initial conditions that end up at this asymptotically stable equilibrium. And here, as Brittany has pointed out, this region gets smaller. And now on this picture, I took E equal F. Now at E equals F, what happens? What's P when E equals F? And Q is still 0, Q is still positive, so you're on a center. Now look, you have these periodic orbits in the neighborhood of this. And actually you have limit cycles. This is a very interesting case that should be examined in more detail. But we leap on immediately to culling beyond. So the last picture is I've made the F bigger than the E. Now what has happened? If the F is bigger than the E, what's the sign of P? Negative. So I've slipped from up here down to here. And what do you see? You're spiraling out. You're spiraling out. You have lost There's no stable fixed points in this whole ecology. Yes?
Does E represent resources available?
Yes, yes. If you go back to the equation, forget the x, y, and the f term for the moment, then the rabbits will go to a size 1 over E. So that's the limit. It's what we called, I think, capital K in the earlier models, okay? It's the limit of the number of rabbits that the resource can support without any other influences.
So what would happen at constant f? If you like increase d to the equilibrium point, would it shift diagonally?
If I did what, sorry?
If you increase d at constant f, would it shift kind of diagonally out this way?
No, no. The fixed point is always 1, and 1 minus E minus F. So it would just move up and down on the line x equal 1. So you can increase E or decrease E, and you just move up and down on the line x equal 1. Yes?
So as far as hunting, is the center what we want to avoid, or is that...
Oh no, no, that would be sort of, it'd be desirable to get in here, because you'd like some, you'd either like it to come into some fixed point, or at least to stay in the neighborhood of some fixed point. What's undesirable is that you lose everything. So sorry?
So the best thing is when E is equal to F?
No, because the trouble when E is already equal to F, it's true that you're getting centers here, but the basin of attraction is very small. You know, you really, if you happen to get a perturbation in the number of rabbits out here, you're going to lose everything.
So how, I guess I'm giving a number, but how do we figure out
What the perfect amount of culling is? Well, I would say something like this, I would think was reasonable. What you'd ask is, what you want to make sure is that due to just random fluctuations, you never want the population to get outside of this basin of attraction. So you'd do the engineering thing, you'd stay well inside. Yes?
So basically you're saying that would a good way to approximate this...
I'm sorry, you're going to have to talk up for, yeah?
So would a good first approximation to finding the optimum level of culling be one where the separatrix still intersects with the x-axis?
Right. Well, actually, if I made F 0, if I had no culling, the basin of attraction would be everything. So, but that may be undesirable, because I may end up with, I mean, if I can get quickly to the fixed point, I might be happy. Okay? But you get random fluctuations of things. And so, you know, there's a trade-off. You're going to trade off a big basin of attraction so that fluctuations won't suddenly throw you to a zero population of predator and prey. But you want some culling because you don't want too many rabbits around. Right? If there was a random fluctuation. I mean, it could happen that you get a very rainy season, get lots of growth, the gamma would change so that it could support a lot more rabbits. Okay. Right. You want a decent basin of attraction, and now if you take out the E and the F altogether, then you'll get just the predator-prey model where you get cycles. Everything is like it's a center. It's like the case where E equals F. Okay. So, but to just summarize now briefly before I leave you, what we've done is we're learning how to analyze this very nonlinear system in the neighborhood of the equilibrium points by setting x equals xe plus capital X, y plus capital Y. We then get linear equations in capital X, capital Y, and the solutions of these linear equations will tell us what will happen in the fully nonlinear system if we start near these equilibrium points. Now I'll talk a little bit more about stable and unstable manifolds next day, but I want to spend most of Tuesday just going over with you in some detail the expectations for the final. So I would like for you to have at least by then have taken a good go at many of the questions in the trial final, so that if you have questions you can raise them. All of next week you'll have 5 tutor sessions, you'll have your own TA session, you'll have your recitation sessions, and I'm available on Wednesday and Thursday, plus the day before the final I'm available from 10 to 12 in room Math 501. That's Tuesday the 17th. Okay.